Right, let's come back to this project here. It's an analog joystick directly from the Allegos Arduino box. It's just 2 potentiometers, a very simple joystick. So I give you the very first task is to play with it so you know what's the output of this joystick. So if you look at the output, it's ground, power, 5 volts, RX, RY, and switch. So switch is there's a little push button on it, so you can push it and send a signal to the switch. So you can see it's being connected to digital pin 2 to sense that switch. But the other 2 outputs, they are shorted to A0 and A1. So they are just an analog voltage output. That's why you need ADC to digitize it. So you cannot directly connect these 2 outputs to the digital pins because they're analog signals. All right, so you need to digitize it first. The Arduino's ADC has a 10-bit Arduino chip has a 10-bit ADC on it, and there are 6 analog inputs that I can use. Yeah, so we used 2 of them. And if you read it into the serial monitor, you can find the range of the output from this guy is simply 0 to what? 1023, right? It's a 2 to the 10, right? It's a 10-bit ADC. So it digitizes the 0 to 5 volts into 0 to 1023 digital steps. So totally 1024 digital steps for the ADC. And you don't have to worry about all the different angles. If you move to the left, there will be a voltage output on the left side. It's just 2 potentiometers, one on X and one on the Y, right? When you move it, then it's going to output an X and Y value, which is the voltage divider's output from the resistors. Very simple. And you don't need to worry about the mechanics inside it. Just look at the output. Since everything got digitized, just look at the digital output and program from there, right? It makes things really simple, okay? And pin number 2 is connected to the switch of this joystick. So we'll push it. It's going to detect a rising edge or falling edge. Doesn't matter if it's a falling or rising edge because you can always debounce it and read it into your controller. Okay, so the first task is just to be familiar with the joystick's output very quickly if you haven't played with in the past. Okay, so the reading x-axis if you don't do anything, so you can see it's not perfectly designed. There will be a little offset. It's a mechanical part, so it can be a little bit off from the middle. So outputting a 4 for the Y, and X is outputting a 521. Okay. If you maximize it, you can see push to one end, right? It's going to output a maximum value for the Y. Okay, and starting from the second section, it becomes a bit trickier because we used to use the it's called Open Smart 2.4 gigahertz transceiver. It worked pretty well. However, this component discontinued, and I have to wait for like a month to get it shipped from AliExpress from China. So, and even that, I think the original vendor from China is still trying to discontinue the one which is only available on the market right now. So in the future, I think we are not going to use this transceiver at all in the future. So we'll switch to the NRF 24 module. It's very similar module, and you don't even need to care about what's going on inside the circuit because everything is just packaged into the libraries. Um, you just need to worry about the digital pins, right? Is it UART like TXRX or is it SPI? It's all digitized. Just follow the digital protocol. So if you use SPI, just load the SPI.h into Arduino, and then directly read from SPI, so you get the bytes. Very simple. And the wireless thing is all handled by the module, so you don't have to worry about the antenna and the wireless protocol on the board. It's just a module. Grab it and use it. Okay. But you can imagine that if you have it's a transceiver, which means it's a transmitter and a receiver, just same module. And if you send a signal, it's mostly just to have a print function. So you can send the signal through here. So it's going to receive the byte and being processed by all the chips on the board and send it through a wireless protocol to the air. And the same thing if it's receiving, it's going to receive it and then eventually digitize it, and the data will be a byte available at TX. Okay, so it's going to send things out to Arduino. So TX is transmitting, RX is receiving. Okay. So what I did over here is I use a joystick and send a signal. It's the analog signal being digitized by the Arduino's ADC. And the Arduino's ADC convert it into a digital signal, and I send the bytes through UART using this wireless module, send it out, and use another Arduino to receive it by this receiver. It's the same module, but you use it as a receiver. Okay, so this guy receives the wireless signal and convert it into the byte and then into the UART TX byte being put into the TX buffer. And you don't need to worry about that because everything is handled by the library, right? So TX will be able to handle that byte and send it to your Arduino through UART. So that's what I did using this module. And that's a second task. So the first task, keep in mind the first task. So we're going to have a little bit more than a week for this project. It's going to be today is Tuesday and next Tuesday, I think. Let me see. Yes, due next Thursday, right? So you have Tuesday, Thursday, and next Tuesday, and then Wednesday after that. So it's next week until won't do until next Thursday. So the first task is the joystick, very simple, and read into the monitor, so you know how to use the joystick. That's the first task. Okay. The second task is do the same thing, a joystick with a microcontroller, and then transmit it using the wireless module and receive it by another one and store it in the Arduino and directly display them in the serial monitor. Okay, so here's sending wirelessly and here's receiving wirelessly and directly display in the monitor. Make sense? Still just constant, not constant, but just simple numbers. I don't know, $2 is fairly cheap. And the third task is to use joystick to control a stepper motor. And the tutorial for stepper motor is here. So skip this one. They're not using this one to drive it. But we're using the same stepper motor, okay? It's called NEMA 17 stepper motor. So see this demonstration, I have the code already provided in this tutorial, but we are not using this driver because it's pretty bulky. We're using this one instead. So I have a box in the lab, probably has like 20 or something of these drivers inside. It's way smaller. I use this driver to control the stepper motor. I have the hardware connection already provided here. And you can see it's working. So here's the driver with a little heat sink on the top, because this motor is consuming a lot of power and current. So you use the code here to build a circuit like this to drive it first. So take baby steps. Okay, so if you can drive it using an Arduino, then you can use the Arduino to receive a variable from the wireless module and then control the stepper motor indirectly. Okay. So we are basically building a little remote controlled, it's not a car, but it's a stepper motor. It just didn't put it on the car. It's actually a remote controlled car using a wireless module instead of Wi-Fi, like what we did for the ESP32, right? So now it has to be, everything has to be offline, okay? And you don't need any Wi-Fi infrastructure that you can directly use these wireless modules in the box and sell it, as a toy without any Wi-Fi connections. Or camping, in the woods, you can still control. Or if you are, driving a remote boat, like what Mason and Ian are trying to develop for the kids, right? You can directly deploy these boats in lec9, right? Drive it, use a little. Okay. You don't have to worry about these parts in this tutorial, because this is for the two-wheel balancing robot. I'm going to introduce this later, but let's just so for this tutorial, I think I have the code, like all the, like for example here, for the stepper motor. There's one thing you need to understand how this guy works. If you look at the data sheet for the stepper motor, I think it's here, right? So that's a snapshot of the data sheet of the stepper motor. So it has, when you program it, you are actually increasing the steps into it. So the reason it's called stepper motor is moving by single steps. Okay, so every step has a different angle. So one one rotation, one resolution. So one 360 degrees has 200 steps if you look at the data sheet of the stepper motor. So each step is only 1.8 degrees, very small angle. So which allows you to accurately control the position of the motor. Instead of a DC motor, you turn it on, you don't know how much angle it spins. You know what I mean? The stepper motor is very accurate because it increases by every single step, which is 1.8 degrees for each step. So you should know that, have that in your mind. You know every single step is 1.8 degrees. And when programming, you can see I move it by 50 steps, I think, if I'm correct. Step speed 50. It's all controlled by the library, because there's a stepper.h library, which handles all the degree translation. So there's a variable you need to set up after you include this header file. And there's another library you can directly use. There's the pins being connected to the stepper motor from your Arduino controller. I think that's the number of steps. So 2 steps every loop. So when you play with it, you can change these variables and see how that affects the speed of the stepper motor. Okay, if you scroll down to our last section, this shows the pinout of the NRF24 module that you guys are going to use in the lab. If you zoom in, you can see it's not UART, because it doesn't have TX and RX. and instead it is SCK, missile, and MOSI, master L, slave E, master in, slave out, right? And that's a clock. So that's a standard 3 connections for SPI, serial parallel interface. It's a standard digital interface. It's very simple to program because the example is already provides all the libraries for you guys. So we are not at the point to program every single protocol or timing by looking at the timing table of the SPI. So now it's just basically just using microcontrollers and existing libraries. So make the connections from your Arduino. You have to find out what are these pins, the SPI ports on Arduino, and make the connection. And you need to use the digital pins. You choose whatever you want to use, okay? As a chip enable or chip selection, but N, so chip selection. A lot of times, if you want, so all the ICs will give you a chip selection or chip enable pin in order to enable or disable the chip without power off or power on the chip. Because if you turn it on and off, it takes time to restart all the little registers and things inside. So usually you keep it powered on, but you can enable and disable that chip or the port by giving a signal, specific signal to C or CSN. So C, if it doesn't say anything about like N or didn't draw a bubble here, which means the chip enable is going to be a logic 1. If you put a high here, it's going to enable the pin. If you put a 0 here, it's going to disable it. But for CSN, it's the chip select, CS. So N is 0 active. So I have to give a logic 0 or ground it to enable the chip. But sometimes the C and CS are enabling the entire chip or enabling a certain transmission protocol of the chip. For this specific module, I think you can look at the description from the data sheet of the module. So CE is an active high pin. We enable, the chip will be enabled. So CE has to be high, okay? So CSN is active low pin that is typically held high because, interesting. When the pin goes low, begins listening. Okay, so you want to always keep it selected. So whenever it's being used or you want to listen to something, you put it low to do a chip select. That's pretty interesting. You know, you think about if there are many wireless modules are listening, right? So you can actually disable it, but only have one which you want to use to be enabled. So the wireless signal will be received. You couldn't control the wireless signal in the air. It's just everywhere. If one transmitter is sending out signal to the air, right? So you can control this pin to make it start listening to the data. Okay, but everything is being packaged into libraries, and I provided a sender's code and a receiver's code. You can see the specific functions to be used to send signal out and to receive signal. And I think this pair of scripts are used to even control the stepper motor. So you can use part of it if you have for the second task where you don't have a stepper motor in there. And also it may work for your stepper motor task as well, but you have to modify the some of the pin assignment if you have a different connection in your hardware. So examples and functions are provided, but not exactly for task 2 or task 3. They are just examples so you can find out the functions and how other people programmed it in the past. Okay, so section 1, so for the tasks over here, so section 1, 30 points, show the demonstration video on your website, which is the joystick controls, send signals to the Arduino and display on the monitor. So it's reading joystick's analog value. That's task 1, very simple. Okay, 30 points. Again, don't show your original code on your website, but put a link where the code is located at, the link on our website. So I know where the code is on the server, so I can look at it. Okay. And for section 4, which is this section. So this section doesn't have specific tasks, but I have to look back into section 2 and 3 to repeat the results in section 2 and 3 using this module to replace the OpenSmart module, which is a obsolete module in there. Just replace that one with this one, which is available in the lab, and finish the similar tasks. So you are, instead of using the OpenSmart module, you are using this module to do the transmission, right? And also control a stepper motor wirelessly. Is that clear? So 3 tasks, 30 points for each, and the report writing is 10 points. All right? And same to all the 3 tasks. Don't show the code directly on your website, but show the link on the server. Okay? Any questions? Okay, let's go back to the lab. I'm going to show you where the parts are.